activities you can enjoy here on Earth is standing still. When you stand still, your position does not change. I'm not displacing any distance over time, so my velocity is 0 meters per second. We often refer to this here on Earth as stopped, being at rest, or chillaxing.
When you're standing still, you can describe the motion a couple different ways on a couple different graphs. On a position versus time graph, when I'm standing still, my position does not change. So I have no slope. This could be 0 change in position here, or if I'm standing a little bit ahead of my starting line, I'd be stopped in a different position. When I look at a velocity versus time graph, I'm really saying a constant velocity of 0 meters per second. So that means at every single point throughout, I need to be on the x-axis because that's where 0 meters per second is located. Since I'm not changing position, I'm not changing velocity, I have no acceleration. If I'm standing still, I have no acceleration. So for my acceleration versus time graph, I'm on the x-axis as well. 0 acceleration.
Earth allows us to do this because of the gravitational forces between myself and the actual planet. We can calculate this gravitational force by multiplying Earth's gravitational force constant, 9.8 meters per second squared, times the object's mass. There's another force acting opposite to that, pushing up on me. Because I'm on a surface, there's a normal force. Normal forces act perpendicular to the surface. They make a 90-degree angle. Gravity's pulling straight down on me towards the Earth, and the surface is pushing up on me with a normal force. This allows me to stand here on Earth without being squished down by gravity or pushed up by the surface. These balanced forces allow me to stand in one place.
The acceleration due to gravity is always negative because it wants to pull you downward. In the case of this baseball, it slows down on the way up with negative acceleration, and it speeds up on the way down with negative acceleration. The big difference is that its velocity changed. It was going up. When my acceleration and velocity are opposite, I slow down. On the way down, it's moving downward, negative direction. When my velocity and acceleration are in the same direction, my object speeds up. Using forces helps us explore the dynamics or the why of an object's motion. Why is this object sitting still? Because gravity, our gravitational force, is pulling down, and a normal force, the surface, is pushing up. That's what keeps it in position. We can calculate this. We can quantify it using our formula. We know the acceleration here on Earth is negative 9.8. We multiply that by our mass, and it'll give us our gravitational force. So if our mass is 72 kilograms, we end up with a gravitational force of negative 705.6 newtons. We can even find how much the ground is pushing up because it's not moving, because nothing's pushing or pulling more, because we're constant velocity. We can assume it's the same but positive. So again, direction matters. The gravitational force plus the normal force has to equal 0. That's how I know it's balanced. So when I add 705.6 to both sides, that's how I get my gravitational force's normal force. 705.6 up, negative 705.6 down.
As I'm standing here on Earth, gravitational forces pull straight down on me. The surface creates a perpendicular normal force pushing up on me. My vertical forces are balanced or equal. Because nothing is happening to me horizontally, my horizontal forces are also equal. 0 equals 0. Some other forces that could act on me. Anytime I have a general push or pull, we would call that an applied force. If that force involves a rope or a string, we would call it a tension force. Right now, my feet are rubbing against the ground, creating a friction force. That friction force can either be kinetic or static. I'm not moving, so this is static friction. Newton's 3 laws also apply to standing still. Newton's first law: an object at rest tends to stay at rest, unless acted upon by an outside unbalanced force. My forces are balanced in all directions. I'm an object at rest, I'm going to tend to stay at rest, unless acted upon by an outside unbalanced force.
Newton's 3 laws of motion. explain motion throughout the universe and are observed here on Earth. They were observed and recorded by Sir Isaac Newton, that guy who didn't actually get hit in the head by an apple. His first law states that an object at rest tends to stay at rest, and an object in motion tends to stay in motion, unless they're acted upon by an outside, unbalanced force. In other words, it takes a new push or pull to change an object's motion. This is one of two laws that helps us understand balanced forces. Newton's second law helps us understand unbalanced forces. An object's net force represents the difference between opposing forces. In other words, it's how much more or less a force is pushing, compared to the force pushing in the opposite direction. Newton's third law states that for every action, there's an equal but opposite reaction.